Thank you and welcome. So, first of all, we would like to present you the KUKA in general and which tasks do we have in the project and the title of the workshop, so it's flexible production using single and dual arm systems. Yeah, so I will begin with the introduction. Some data about KUKA. So we are a German company. We are located in Germany. So the headquarters are also in Germany, in Augsburg. It's close to Munich. We have 14,000 people worldwide. R&D facilities are in Germany, Hungary, and China. So we are known as an industrial robots manufacturer. Also, we have different robots in our portfolio, so mobile robots and cobots, and also we're developing the software for the robots. So KUKA Group contains 5 business divisions. So KUKA Systems, Robotics, Swisslog, Logistics, and Swisslog Healthcare, and China. So KUKA Robotics, we are from KUKA Robotics. We are working on developing the products for robots, so designing the robots, mechatronically, and also software, also small cells, and of course services. The KUKA Systems, it's the system integrator, so uses KUKA robots to build big production lines, for example, for automotive industry. Then we have a company which belongs to KUKA. It's Swisslog, so 2 divisions, logistics automation and healthcare. Healthcare, of course, it's about health, so clinics and so on, and logistics, warehouses, and automotive forklifts, cranes, and so on. And a very big facility we have in KUKA China, which is working just for China market. So our focus industries are automotive, of course, so it's clear. Electronics, general industry, consumer goods, e-commerce, and healthcare. Almost in every country we have representatives, we have sales, we have services, but as I said already, so the headquarters are in Augsburg. Here you can see the small just an overview of our portfolio of robots. So the orange robots are industrial robots, 6-axis robots. Then in the middle you can see delta kinematics and SCARA robots, which we can use for special applications. And on the right side you can see 3 robots, cobots. So first from the right side, it's an EVA robot. For medical purposes, is the certified robot for medical applications. The second one is industrial version of the EVA, and the third one is our easy cobot. So 2 right robots, they have 7 axes, and the third one, the cobot easy, has 6 axes. Right now we have several European projects, and one of these projects is SMARTHANDLE. And the KUKA tasks here, multi-arm motion planning, how we can organize the work of several robots together, also path planning and so on, task-based programming, how we can make programming easy to use, using description of the tasks and so on, and AI-based grasp planning. So how can we increase the grasping ratio, the grasping success, for example, not just for industrial objects, but in general. And now I would like to hand over to Giuseppe, and then he will continue with the first part, dual arm system for aluminum profile handling. Thank you.
Perfect, thanks. I guess I'm starting to share right now. Okay, so I'm Giuseppe. As Kirill introduced me, I'm going to present our work and results in the in the field of dual arm manipulation, in particular for a specific use case referring to the SMARTHANDLE project. That is the one provided by the company Alumil. So Alumil is a Greek company, and they are working on production of aluminium profiles of different shapes and of different lengths, and they have to be then finally packaged, palletified, put on a pallet, and then transferred for delivery. Most of these steps are nowadays still done by human manually, and our objective is to approach the automation of these processes. To do so, we developed a test bed for our technology that we are going to provide to our partner as well inside the project. To do so, we developed this, we set up the current scenario that you can see in the picture. We are using two LBR EWA that are, as Kirill already said, cobots, and are for industrial use cases. These particular robots have 14 kilograms payload each. And in our scenario, we have two of them with two robotic gripper that are two gripper with 3 fingers, together with two cameras from Roboception, V-score that is looking far away from top the working area, and the VSAR that is placed on top of the torso. This second camera can also be moved using a pan tilt unit from Schunk. And finally, we have an application PC that we can use for deploying and testing all our technologies. This is what you are going to, I'm going to explain how we are able to perform the task that you are watching right now. So to autonomously grasp the aluminium profile, so recognizing the pose of the profile itself, so the grasping, the repositioning, and placing. The application follows this the sequence that you can see here. So we start with a selection of the aluminium profile. This aluminium profile is selected using a small web UI that we developed internally for this use case. We need to specify the profile that we want to handle together with the camera that we want to use. After that, we proceed to the detecting phase, in which we find and estimate the pose of the profiles that are available in the scene. After that, we select how to grasp the object, and these steps will be clearer, of course, in a while. But yeah, so we decide how to grasp the object. And finally, we plan and then execute the motion that you already seen in the videos before. So we go on the object, we grasp it, we actuate the gripper as well, and so on. So how we decided to approach the problem is using the following architecture. So we are trying to approach an architecture that is mostly service-based, with a central node that is our main application that can talk with multiple servers. Why we are using multiple servers is because in this way our technology can be tested and used in isolation, and then easier provided also to customer and partner in projects. For example, our grasping pipeline is handled using the 3 services that are shown on the left that I'm showing right now. All of those services are based on ROS technology and are encapsulated into Docker images. This makes it easy for us to deploy them and to test them in different situations and in different demos, for example. We have then, of course, technology also for getting images and point cloud from the camera, together with the 6D pose estimation. This is using Roboception technology, as we are going to see soon. And then our planning and motion execution procedure that is shown here with this linear motion planning, collision-free motion planning, and the synchronized motion execution. So let's start describing part of this application. Let's start with the perception part. Regarding perception, we are encapsulating into a service the Roboception CAD match functionality. This is a technology that Roboception allows to use with their camera to get pose of objects that are previously learned by a model that they train on site. So the procedure is we send a model to them. They train their AI model in such that they can find the pose of this object into the scene, and then we can deploy that on our system. And we are in a close collaboration with them in order to improve the templates that are that they give us to recognize the object in runtime. Then let's talk about the grasping pipeline. So the grasping part is divided mainly in two components, the grasp sampling and the grasp evaluation. Why are we dividing these components in two? Because we can decouple these two logic and try to pre-compute as much as we can. So for example, in our scenario, we have the grasp sampling that happens only once and only at startup. So it's something that does not have to happen in runtime and can take even longer time. The grasp sampling, the technology used for grasp sampling will be briefly shown. Here we are using them to generate grasp poses, so configuration of our gripper, and storing them. Then at runtime, what we do is to take some runtime information like the point cloud and the object pose, together with the grasp poses that we sampled and stored beforehand, and we have, after all, the assorted list of grasp poses. They are sorted in terms of score. So the grasp pose that has highest score is for us the best grasp that we are going to try to perform. And this is how a grasp, for example, may look like to us. Assuming that we are having a parallel gripper, our grasp is defined into object pose and is object relative. So the grasp itself can be computed using only the information on the gripper and on the object. How are we sampling the grasps? Well, we are using two different methodology. One, the simplest one, is the approach sampling. The approach sampling is based on a very simple situation. We take the object mesh and we sample point on the surface of the object. Then we approach with our gripper, with the approach axis of the gripper, this point, and we try to check if the object is between the finger. If this happens and there is no collision, perfect. We have a grasp sampled for this object. Methodology that is a bit more complicated but giving also better results is the antipodal sampling. In this case, we are still taking our object, the mesh of this object, and sampling on the surface on points. But then we are using these points, and in particular, we sample one of those, and we compute the normal of that point on the surface of the object. Using this information, we can try to project this point on the other side of the object. Why? Because we are trying to find two regions of the object such that they can be used together for grasping. So a region that is from one side and another region on the other side. If this happens, so if we are able to find two regions like that, it means that we can approach these two parts with the two fingers of our gripper. And this is how we sample using the antipodal methodology. We then use all this grasp only if there is no collision between the gripper and the object itself. And here is how so that the approach that I just explained works just fine for one object, but how do we enhance this approach with multiple objects? So for example, in this case, you can see some grasps sampled for this aluminium profile. So the way we do so, it will be shown in this simple flowchart that I'm going to present. So we start with loading the object model, and using the object model, we load also the gripper, and we try sampling one of the poses of the grasp. This means we can use one of the technologies that I showed before. Could be antipodal approach, or could be the approach methodology. After that, we sample the grasp pose. We check if we are in collision with the environment. What do I mean with environment? In this first part, I mean simply the object itself. So we are checking if we are in collision with the object. If this does not happen, so if we are not in collision, we proceed to add the gripper to the environment. So we have sampled one of the grasp poses of the gripper, and we will proceed then with the sequential steps. Otherwise, we try again with the same gripper. If we finished with all the grippers, then we are good to go. But if this is not the case, we add the second gripper and we start again. So it means with the second gripper, we sample some poses and we check if it's in collision with the environment. In this second case, then the environment is represented not only by the first gripper, but also by the not only by the object, but also by the second gripper. And this is how we then finish the algorithm. If we sample a pose for each of the gripper required for the grasping, then we have now our multi-grasp sampled. Then how do we make it work in runtime? So as I told you, we perform the sampling offline, but then we have to choose at runtime which is the best grasp. You can see here on the right side the information that we are using for evaluating the grasps at runtime. What we are using here is the gripper pose itself, the point cloud, and also the pose of the object, because then the gripper are placed where the object is supposed to be, or is where the gripper is, where the object is recognized. How do we score our grasp? Is shown in this equation. So the score of a grasp, indeed for us a grasp is a multi-gripper grasp, so it means grasp poses for all the grippers included, is the minima between all the criteria and all the gripper. Let's suppose to have n gripper and m criteria. We evaluate all our criteria that are heuristics for us for each gripper, and we take the minimum of all of those. The criteria that we are considering right now are the grasp direction. So we define a desired direction D, that in our case, for example, is the z-axis that you can see from the back in the videos here, the blue axis. That's the direction that we would like to grasp from. Given that, we assign a score of 0 if we are approaching the object from a completely different direction, and we check it via a tolerance. Otherwise, we compute the score using the following equation. That is a linear equation into the angle between is an equation that is linear, a linear function of the angle between the approach axis of the gripper and the desired direction. This score goes from 0 to 1. The same applies for the collision. We have another heuristic for that. That is very simple: 0 if the gripper is in collision, 1 if it is not. In this way, we are able to find grasps that are aligned to the direction that we would like to have and are collision free. Of course, other criteria can be added, and we are working on that, like, for example, the stability of the grasp or the weight distribution, and moreover. Then, after that, we decided which is the best grasp for the object. Then we need to we have to plan the motion. For doing so, we use two components. The first one is inverse kinematics. We know where the gripper should be placed, but actually we don't know which joint configuration for our robot is the one performing or achieving that pose of the gripper. So what we do, we use a quadratic programming-based inverse kinematics approach. So we use a QP solver to find the desired configuration of both manipulators. And then finally, we use Open Motion Planning Library, OMPL, to plan a collision-free motion from the starting pose to the grasp pose. OMPL wraps contains the implementation of a plenty of sample-based algorithm, like for example RRT or PRM, and all the variants, for example also RRT star. Moreover, they check for we can check for collision-free and also some distance checks if we need distance information using libraries like FCL and COL. But the QP solver and the QP-based approach is not ending only for the inverse kinematics, but also for the final part of the motion, or the part that is nearer to the object. Once we have a motion that is collision-free and is above the object, what we would like to have is to go down straight to the object itself. To do so, we are performing a linear trajectory, and we are injecting a trapezoidal velocity profile on top of this trajectory. Again, is a Cartesian trajectory, so we need to find joint configuration that are able to perform these collisions, this Cartesian space trajectory. To do so, again, we use our QP based approach. And the QP-based approach is not used only by us in this specific scenario, but is used in our department for several applications. For example, you can see how we can enforce something like geometric constraints. For example, two planes being parallel, as you can see on this right side here, or performing a very long trajectory, ensuring that we are inside the joint limits all the time. As you can see on the left side. More details about the QPE-based approach, and in particular how to enforce Cartesian constraints, will be then assessed by my colleague Martin in the second part of the presentation. Then finally, when we planned all our motion, we are ready to execute them. And how to perform that, we use ROS2, in particular ROS2 control framework. And we are using the open source KUKA drivers developed by our colleagues in Hungary. They have the set of libraries that you can see on the right side on GitHub, and with minimal adjustment, it is possible to use this library for synchronized execution of motion on multiple manipulators. Why is this important? Because simply we are not in a scenario in which all the robots are connected to a single controller. Every robot here is controlled by the individual controller, and that means that it's not guaranteed in every moment that the motion is synchronized. But in using the tool developed by our colleagues, together with ROS2 control, it is possible to perform synchronized motion on multiple manipulators on several part. One of those is the motion planning. We are planning right now motions individual for each manipulator. So it means that for even though we are using them together and we are planning them the motion together, so we plan joint values for all the robot, we are not planning this independently on the robot itself. We would like to plan the motion, for example, of the aluminium profile, and then independently of the kinematic chain that we have, we can perform the motion. To do so, we can use our QP-based approach together with some other technology that our colleagues are working on. In particular, SCLERP algorithm, that is a screw linear interpolation. So using screw theory, is it possible to interpolate frames such that they're consistent along the motion. An example of the problem that may arise using simple linear interpolation is shown in the figure here. So if we define two different points, two different frames, referring to the same object, and we interpolate the motion between some key points, for example here, A1, A2, and finally A3, we can simply interpolate those frames and have a trajectory, a Cartesian trajectory out of it. The problem is, if we take the second point, B, for example, and we interpolate at the same way, the in between the two via points is not guaranteed to be consistent, and that can cause a stress on the object while manipulating with the dual arm system. So using screw linear interpolation, this is not happening anymore, and you can see this result from the right side. What you see here on the bottom part is some initial promising results using this interpolation technique into simulation. And we are going to integrate this into our setup. Finally, what are the challenges that we are going to address in the near future? One is the pose estimation. So the CAD-match technology provided by Roboception is based on the CAD model of the object itself and requires training every time we want to manipulate an extra object. So it means that we have an overhead every time we want to add an object to the set of objects that we want to handle. To do so, there are several, to solve or mitigate this issue, there are several approaches that can be found in literature, but moreover, another important problem that we want to address is the accuracy, because some error in the 6D pose estimation of the object may lead to a wrong or an inaccurate grasp strategy that brings them to an inaccurate placement of the object into the placement position. And that is, in our case, an important problem to address. Then also the grasp sampling itself is using right now, as I showed you, geometric-based technologies. We are working in this moment on evaluation of several AI-based solution. Why? Because AI-based solution may reduce the amount of grasp that we need to sample to have sufficiently high quality of the grasp itself. Because what can happen? It can happen that we have sampled, I don't know, 100 grasps or 500 grasps for a specific object, but by luck, all those grasps are then not of high quality. What do I mean with high quality? Well, it depends. Right now, we are checking only for collision in our sampling, and it means that the grasp itself may be not stable. Using zero-shot technology or few-shot technology, like the one based on diffusion models, can be then it can improve the average quality of the grasp itself and reducing also the runtime cost for evaluating them. Finally, we are trying to tackle the problem of deploying robot application also in a modular and innovative way using service-based structure. That's something that is more than known in web application and in several domains, but in robotics is something that it's getting more and more useful. But this implies also problems. For example, in a simple monolithic application, okay, we have a big monolithic complex application, but the component is just one. Here, when we have several components, as we showed you at the beginning of this presentation, we have also the burden of maintaining the communication between them, and we have the complexity of the networking as well. And it's then get also harder to debug one of those individual components, one of these services itself. Moreover, we need then orchestration. That is a new task, that is something that can be approached using, for example, solution like Kubernetes that is providing helping to, for example, ensure availability of the services itself, and this together with Docker may make possible to have reliable and reliable application, where if there is a component that by any chance crashes, we can make it turn on again and available to the user again. And with that, I finished my part of the presentation, and I'm looking forward to questions.
Thank you, Giuseppe. So we are good on time. So now we have time for several questions. I can't see any question in the chat, so just if you have any, just ask for it now. Okay, no questions, but then I have several questions. So you explained us the dual arm manipulation. So you're using two robots. So the question is, are you using one controller or two controllers? And what are the advantages and disadvantages of using one controller or several for each robot?
Okay, so we are using right now in the setup that we built here several controllers. So we have one controller for each robot. Why are we doing so? Because in this way, if we develop technologies that can work with individual robot without knowing exactly which controller are they running or stuff like that, we can develop technologies that then can be used with the entire portfolio of KUKA, for example. And they are not bound to a specific scenario in which we connect more than one robot to the same controller. Of course, having multiple robots on the same controller simplifies some part of the architecture, because then the synchronized motion execution is implicit and is trivially handled by the controller itself. But that may generate issue when we want to use, for example, some components that are capable to be used with the controller, and some other components that cannot. For example, if we have some external access or external joint that cannot be handled by the controller itself, with this way, with this synchronized motion execution, we can still perform the motion.
Can you also combine several robots, different types?
In this current scenario, yes, because we are relying on the ROS2 control framework. It means that with some minimal adjustment, every robot that can be used with ROS2 control can be used synchronized together with other robots.
So actually, you can use one 6-axis robot and another one is 7-axis.
Exactly.
Okay. And another question is, so you presented the grass planing and you presented just 2-finger gripper. Is it also possible to use 3-finger or 5-finger gripper?
So yes, we are right now, we have a gripper that is indeed a 3-finger gripper, and is moreover even under-actuated. So the kinematic model of the gripper itself has been simplified in our scenario in order to be used as a parallel gripper. The technologies that we have in-house right now are able to cope quite good with parallel grippers, but we are definitely looking into a scenario in which we are going to use more complex grippers.
Okay. Yes, thank you. So no comments from audience? If no, so I will hand over to Martin and he will present the task-based programming.
So thanks, Kirill. Hello together. So give me 1 sec to share the slides. Let's see what it is. Introduction should be this one here. Are they still shared in? Yeah, full screen, thanks. Okay, so let's go so in SMARTHANDLE we have 3 use cases. One was presented by Giuseppe. This is this aluminium use case with aluminium profile handling. The second one is for contact lenses to produce them, and I will present the third one. That's also interesting for KUKA is this AB use case that we can disassembly car batteries. So what you can see on the right is a battery, and there you see different things. And what we want to do is with this battery, we want to disassembly then, and you have different steps for that. So the first one is already done. So it's discharged already, and also the battery housing is removed. You see here where the bolts were beforehand, and then it's removed. And then you see here a lot of cables, and additionally also I've seen here some cooling pipelines. So that's things that have to be removed. And there's also a battery management system inside the battery that you want to have removed additionally. And then in the battery, it's separated in different modules. You see here some of these modules here, and we want to extract them and then recycle them. So that's what in general we want to do in this AB use case. And for us at KUKA, especially interesting is motion generation. And for that, we are doing this unscrewing of this housing. So if we go to the next slide, if you go to the slide here, so we have a test bed at KUKA for this unscrewing bolts. So it's currently very simple, as you can see it here. We have some screws and they are there. And what we want to do is we want to have one robot that is doing the unscrewing part and a second robot that is doing the grasping of the bolts. And if they are grasped, then throw them away. And that's during the unscrewing process, of course. And for the hardware, we have on the left side a LBEC and some simple gripper, so a shoe gripper. And on the other side, we have LBIVA, plus we have Apex screwdriver. It's a prototype with a Cleco controller. The Cleco controller, yeah, it's on the bottom of this picture here. And this with this screwdriver, you can also generate torch. So it's not something simple, but a special screwdriver for industrial use cases. And what you will see today is this part of this unscrewing process from this right stuff. So I have one video here. So no, it's not starting. Interesting. Okay, give me a sec. So it's starting. So what we are doing is we are moving to one of the screws, move down, and after that we have a retreat motion. So the screwdriver is currently not actuated, but this will be done in the future till the end of the project. And if you see that, that's really quite simple. So if you ask an application developer, yeah, he will say, okay, I do that quite easy. And how that's done and what we really have behind for the motion generation, I will explain in the next 20 minutes. So if you normally program robots, what you are doing is you see it on the right side in a simulation. So you have a TCP I stop it here. We have here this TCP where you want to move the tool of the robot. And this TCP is then moved with different motion types. So first to P1, then down to P3, you can't see it here, then up to P3 again, and then to P4. So this is what you see here. So you have some PTP and some lint motions. And that's how you normally program the robots. So this is the standard way, not only at KUKA, but also at ABB, Fanuc, and so on. So main thing what you are doing is you're teaching frames. You are defining the motion types, so linear motion, circular motion, a PTP in joint space. And what you also say is you have additional parameters like velocity, acceleration, or you can see it here, you have this blending. So it's not directly reaching P1, but it's blending over to the next motion. So if we look at a little bit from above in an abstract way, so we have the complete path here, we have the tool, we want to move along this path here, and then we have these frames. So if we have a little bit more complicated, so we start here, and here is our TCP currently, and then we continue. and then we are at some point, and then what's happened very often, cannot perform motion. And the reason for that is that we are reaching our workspace of the robot, or even more the access limits. So it's not possible to move to the next point on this path. And that's very, how to say, very sad for the application developer, because if you are here and you cannot execute this motion, then you have to start here and reteaching all these points here. So this is only 3-4 points, but you have to redo it till you find a solution that you can execute it completely. So, and that's and the reason for that is that this programming that we are currently doing is over-specified. So I will explain it a little bit here. So I have one screw here, and we want to reach it with one frame. And if I rotate this screw now here, I cannot even reach this screw or this bolt anymore, because it's out of space of the robot. So the position is the same, but the screw is rotated around, or the bolt is rotated around 180 degrees. And that's the issue. We don't need this rotation around this blue axis here. We don't care about that, but we have to care. We are teaching it. And while we are programming, and additionally, because we have here a 7x robot, we are additionally also teaching more than 6x, more than this point here. We need additional information like this elbow and the top, what angle this is, because we want to reach this point. So if we say that, always with the same orientation and with the same robot configuration. For that, we have to teach this point, this frame as 6D frame plus robot configuration. And this makes it, of course, very non-flexible for processes. So if some parts are rotating, we are not using some robot redundancies, or here this process redundancies. I will explain that on the next slide, what I mean with that. And we are also not using CRD information. So we are also not using collision avoidance. We program, and then at the end, you deploy it on the controller and check it by hand if it's in collision or not. So about this redundancy, robot redundancy means that you can reach one frame here, that's at the top of this bit, with multiple robot configurations. This is possible if you have a 7x robot, or if you have a 6x robot and some rotation tilt or some linear axis, or if you have a mobile robot with an arm on it. So this is quite often that you have this one here. And what you even have more is process redundancies. You can see it for welding here, even in the script you don't care about this rotation. At this point, if it's 60 degrees, 61 or 70, it must be in this range. And furthermore, also this rotation axis you see here, you don't care about. Could be that you also can shift that. But this process information is currently not used with the current programming. And yeah, there are other guys in research. Yes, so there's this one video. Okay, I kicked it on. Give me 1 second. Want to see if I have this video inside here. No, then leave it like that. But I had it. So what we did then is that we said, okay, if the frames are limited, so then say, okay, let's unlimit this frame. So it's possible now to say, okay, that we are moving. This is really, I have some technical issues now. Sad masses. Let me see. I'm not sure why they are not working. What we did is that we say, okay, it's now possible to have this ranges. So around B, it's possible that we have some rotation that's possible, or X and Y. So it's possible, and then more processes are there that we can free them. So one thing could be is that we are in this range here, and it can be somewhere. This is possible. But this has also some limitations, this programming style with this underdetermined frames. So if we want to describe that your TCP somewhere inside this cone here, how do you then write this with, you can only say X, Y, and Z. This is what your frame is. And then at the end, at the end, you have then some equations inside. And this is nothing we can give to a user. So for simple use cases, it's possible to have some ranges for X, Y, Z, or APC. So for example, in our use case with this unscrewing bolts, we can say the rotation axis in Z direction, we don't care. So in the direction of the bolt, then say it's unlimited, and then we find more solutions. But if it's getting more complicated, it's not a solution. And for that, we have there are some research institutes that are doing it differently. They have some programming techniques that are based on constraints, especially geometric constraints. So what they want to do is they want to put a bearing on the stuff here. And what they are selecting here is they select coincidence. So they're saying the bearing must be coincident with this stuff here. And with that, they are describing some constraints. And these constraints are then automatically generating a path. So you see it here. So we have here a robot. First thing what they are doing is they are closing the gap between simulation and reality. So they then exactly know where the objects are. And then they generate it out of this geometric constraints a path. So, and this was from Fortis. Fortis is a research institute from the Bavarian state. And they are doing more things in this direction. And we also have seen that, I'm not sure, 2014 or 15, and thought, yeah, really cool idea. We want to have it because with this technology, you have increasing flexibility. You have this process redundancies. We think that the programming time will be reduced because of this process redundancies. And most important thing is, of course, also that non-robot experts can program. So you need process experts that can program. And to realize that, we need two things. We need one thing that's regarding UI and programming. So we need this geometric primitives and constraints that the user can configure them. And on the other side, we need, of course, algorithms to solve this task description done, or this task described by geometric primitives and constraints. So this is how this structure looks like. So we have on the one side our simulation with the task description, with the geometric constraints and so on. And on the other side, we have our smart motion generator who solve these constraints. And then the scene is synchronized automatically via distributed environment model. And then in the IDE, you can request the robot motion, so sending the task description, and the solver sends it back, and then you have it in this robot simulation, and then you can execute it in simulation and later on the real robot. So what we need first is geometric primitives. There are a lot of primitives in different CAD tools, but they are not standardized. So you have different description for a cuboid, for example, a different one. And in another project, we did a conical representation of these primitives. So even at KUKA, you will find different primitive descriptions for a cuboid, for a cone, and so on. So that's normal. But we implemented we defined a conical representation and implemented in the robot simulation IDE, so the user can configure it. So this is the first thing. The second thing is geometric constraints. Perhaps you know them from your school time, so that you have parallel of lines, you have intersecting lines, then they are perpendicular, or you see here point is on the line, and there are more like that, also with planes and so on. And the main benefits for using this geometric primitives is in combination with this geometric constraints is that you can quite easily compute them. They are not heavy computation, but fast computations. And on the other side, the human can understand them. So you can see it in reality, and you know what is perpendicular and so on. And it has some representation in the real world for the human. And what we then had in one of our projects, we had a list of these geometric primitives, geometric constraints. So that. And third thing we need in our IDE is that we can then move these primitives. And for that, we developed a spline and to that velocity profile. So for the spline itself, it has some nodes. You see them here. So these are some positions. And then first and second derivation at these positions. And this information in combination with the interval type generates this path here. So here you see this Hermit spline, fifth order, and then you have these points here. And on the points, you have the first, you're right now seeing the first derivation. And in combination with the second one, then you can define the whole figure or the whole path of the spline. That's one thing. And the second thing, what we want to have, we want to move a point on the spline with a velocity profile. And for that, normal one are the trapezoidal velocity profiles that are a little bit simple. So we have a better one, a sinus-based acceleration and deceleration or deceleration profile that we can move this point along the spline and use this point later then for our geometric constraints. That's that. Here's a prototype from us from a bachelor thesis where you can see that that currently is the spline is configured with these positions and then with the type. So we have here the spline type and then these points are set up that you want to have. For example, now it's selected to a circular or to an arc type. And yeah, this is done, and then you can define how to say the spline with it. In the future, this is of course done in the 3D to itself, but for a prototype, that's quite valid to have this one here. That's one part of it, and if I jump to the second part, is the velocity profile. So let's go here. It's a little bit. So yeah, let's start here. So we have a velocity profile, and there we can add some accelerations that we want to have. So we have here at the beginning acceleration to 200 millimeters, and then we add a second acceleration to 180, so a deceleration. And then what's happening there is, I stop it shortly. So we have the acceleration here. This is the first part with the length of 200 millimeters. Then we have the deceleration to 180 with the length of 200 millimeters. Of the complete spline, then we have 400 millimeters constant velocity and then 800 millimeters deceleration. So with that, the spline and the velocity profile is generated. So last thing is the task description. So in there's a process path, geometric constraints based on primitives and stop conditions, and I will explain it in how to say, in a step-by-step. So if we have this screwdriver here and we have the bolt here, first thing we want to do, we want to move that the screwdriver is moving along a path. It's this one here. And for this path, we have a point. So at each, this point here moves over time from starting from here to the end of the path. So that's what we have here. So we have the path, we have the corresponding velocity profile, and this is the current time for used for the generation. And for that, we have the point of the path. And then what we are doing is we are saying this tool point and this point of the path should be always coincident. So they should be over each other or should be at the same position. And this then generates a motion starting from here to the end, from the tool from this point here to the bolt. And with this time is then triggered that this complete tool is moving. And second, we have a rotation axis, meaning that this tool should be always parallel to the bolt. And last thing is that we have a stop condition, and we're saying if the velocity profile is completed to 100%, then we are stopping this motion. And to see the difference here, if you only have this tool point here, then you have a tool and it's moving along this path here. We are going a little bit more down because of impedance control. And then we are moving to the right. And if you look at the other side, if you additionally have the parallel constraint, then you are always sure that your tool is orientated correctly. But still you have the freedom to rotate around this rotation axis. So this is not fixed, but it's fixed that you are parallel with the tool to the screw. So that is one part. So this was the UI part, left part. Now we are going to the smart motion generator to especially this QP-based motion planning that Giuseppe mentioned already. So what we have here is a robot, and there we have axis values. These are the Qs, and we have this X, Y, Z, A, B, C. That's the point at the flange. So if we go a little bit over it here, you see here, we have this point at the flange. That's interesting for us. That's we want to move in Cartesian space. And to move that, we need certain axis values Qs. And what we have then here at the end as equation is we have a function of this axis values, and this result of this function must be the same as the position that we want to have. So it's 0 at that point. And if this is then the first equation, and the second equation is about constraints. So we have some constraints that are based on this Q and P, so on this point here. So we call it point of interest. And they should be in some ranges. And if you derive them via time, then you get normal equations that you know. So this one is then the Jacobian matrix. You have the velocity of the axis values. So this is known in robotics, so standard thing. P is derived to, of course, velocity. And at the corner, we have a partial derivation regarding our constraints derived to axis values and to Q, and also our constraints derived to P. And what you can do with that, you can combine them, of course. So this one here can be set inside here. Then you have this equation. And at the end, it's a new Jacobian that defines that it should be in range. So that's very mathematical. Going a little bit into how to get the constraints now inside this mathematics. So what we have at the beginning is we have parallel, a line should be parallel to another line. So this is line. That's what you can do, and from the UI side, and it's understandable. Then you have the equations for that too. The parallel equation is there are multiple ways to do that in math, but one is that you are using the vector of this first one and the vector, the direction vector of the second one, and then subtract the norm, and then say it's equal 0. And this is realize that they are parallel. And then we have the equation from before, this CQ. So out of this equation, we can calculate this JC, and give this equations into our numeric solver. And that solver then is based on QPOASIS. So this is for quadratic programming as solver for that. There are several ones, but this one we are using. And it generates then for us Q dot and Q for each time step. So if we have one for one constraint, we get a solution, and in another time step, we get another solution for that. So here are some examples. So if we have some, I go only on the left because of time. So on the left side, we want to have a laser, so a line going through a point, and we want to be that this line is as an angle between to a surface, so B. And these are some constraints, so it's going through this line, and then the angle should be between an A max and an A min. And that's one thing, one of these constraints. There are others, and if we, for example, have now this angle constraint here, you see it, then we convert it to A sin and say it's A max. And with that, this constraint then go inside our artificial constraints. With that, the solver can find a solution for us. Examples of that are multiple ones here. So here we have some deeper use case of a service. I think the most interesting one is on the top left, bottom left. Here we want to hit with our laser beams, so move along the lines and on 2 lines at the same time. So we have here 2 laser beams here, and then want to hit both of the lines. So programming this with frames, I think, is not possible the current way. So besides this, the geometric constraints, we have additional constraints like collision avoidance, and for that we are calculating the minimal distance between an object and a segment, and this is also put inside the QP solver. And on the right side you see a solution. So we want to move from the left to the right, and the cylinder should be in contact with these 2 lines, and it's automatically avoiding obstacles. And this is done by the QP solver. And this is our constraint solver then, of course. So then with the UI and the constraint solver, we have tested some of these things. So here you see what we want to do is we want to follow with a line, a spline. So on the spline, we have a point that moves along this path. And with that, we want to do it with in simulation and under robot, and we have done that. So it works. So it's possible to define with geometric constraints a task for the robot. So this is done. And what we also additionally had is we have events in the constraints. You see it on the right side. The constraint is only activated if a point is hitting this object. So we have a point that moves along this line in our CAD data, and we have also the object in our CD data. And if the distance between this point and the object that we have here, then we can activate some signals. And with that, we have some events, so we can react to geometric events, for example. So that's the current state we have. So what we are doing now, so to improve all of that is, so planning time is an issue. So we are improving that right now. Then another issue or challenge is that to find valid solutions, we want to increase this probability with better geometric constraints, and also finding, let's say, or improve the mathematics behind our algorithms a little bit. And last thing is also to add additional geometric constraints. So with more constraints, we have more possibilities to realize the task. And for the testbed application, of course, first thing is that we want to actuate also the screwdriver that you have seen. So this is not actuated currently. We want to do that with the robot. And of course, we also want to evaluate the unscrewing process. So what we are doing is we are moving down and then have some impedance and move back, and want to improve that. And of course, we also want to have a realistic battery mock-up. We know that, so this is the things we want to improve and we are currently working on. And yeah. Last slide from my side is now, what are the challenges? So one challenge in general is simulation and reality gap. We are defining everything in CAD data currently. And if you look very closely, you see the derivation between where it should be. It should be on the edge of the object, but it's a little bit besides. So this is one thing. Because of tolerances. So this is this part here is not modeled completely correctly, and then we have some tolerances of the workpiece, and that's not working. The other thing is that we don't know the exact pose where the object is placed. For that, for example, you can use the foundation pose or other object. 60 pose estimations Giuseppe presented today. These are the two things. Then performance, of course, is that we improve that. And last thing is we are currently only doing it for, so we are planning it ahead, but we are doing not doing reactive online motion planning, so we cannot react during runtime, and we want to test if this is also possible. And for that, we have to do some verification with our algorithms if they are really real-time capable and if they can be used for motion control also. And we have to improve our libraries that they are hard real-time capable. Yeah, currently not, but this is more doing than, yeah, we have to do that. So these are the open challenges. So that's from my side. So what you have seen is even for easy motion that you have seen with this screwdriver, you can if something changes in the environment or the screw, the pole is detected differently, then it could be that you're not finding some motions. And with this technology, I've presented you the possibility to find motions and to be more flexible is higher. So then to the Q&A session. Kirill, do you have any questions?
Thanks, Martin. So we have one question in the chat. In which real-world scenarios or industries could the test bed for unscrewing bolts be applied?
So does it mean so the real use cases? So let's go back to this battery. What we really want to do is to first unscrew these bolts here. This is clear, but also go deeper inside. So there could be some parts inside the battery. That's why we have this long bit to go inside that we can also unscrew, for example, the cable holders. That's also possible at some points. And in general, we are not limited to this battery disassembly. It's a general approach that works also in other domains of industrial production. So for our industrial use cases like deburring and so on. And yeah. Is this okay?
Thank you. So any questions from the audience? If not, then I have some questions. So again, about the different robots. So what are the differences for your task-based programming for 6-axis robots or for 7-axis robots?
So I go a little bit through the slides to explain that. This is so what you let's go a little bit more. Give me 1 second, then I can explain it to you directly. So what you see here is that we are independent of the robots. So we are describing the tasks in relation to a tool that's attached to a 6-axis robot, a 7-axis robot, a mobile platform, or whatever kinematic that is there. So we are independent, so we can work on 6-axis robots, 7-axis robots, robots attached to mobile platforms, attached to linear axis, and so on. So we are really independent. This dependence is decided at a runtime. So at runtime, we have, of course, a full scene with the correct attached robot. You see it, for example, here. If you have a tool, then at runtime, we have the complete scene, but at time we are describing this tasks, only the tool is interested.
So you can also consider this tool as the additional accesses.
I wouldn't say additional access. The tool is there, and it's so a tool can have, of course, additional access. Then it's also kinematic. But in general, if you have this tool, it's a tool-centric approach. We are describing the process in relation to a tool, and how the tool is attached to the kinematics is not important for us. For that, we have the algorithms to solve it and to give it a joint trajectory for the kinematic.
Yeah, thanks. And so you showed also on the slide 28, there was an obstacle on the laser line. This is done by Robotics. So is it real-time obstacle avoidance? No.
As I said, we are currently only planning it. So what we had in CRD, also this obstacle here. And with that, we are only planning it. If you're now using your hand and move inside while it's moving, we cannot react currently. This is something we want to develop in the future. This was also on this open challenges. But what is possible is that before you plan this motion, you can make a screenshot with, not a screenshot, you can detect objects with a camera and then plan and then execute. For that use case you can use. But if something is changing during the motion, it's possible to detect.
So no dynamic.
Yes, no dynamic obstacles.
Okay, and the last question is, you mentioned performance of planning algorithms. How can you increase this performance? Like, I don't know, using GPU or something? Or?
So there are several things. You can parallelize them. This is one thing. At least some of the constraints you can parallelize. If GPU is the right thing or not, I'm not sure, because your CPU should be enough because you don't have too many constraints. So if you have more constraints, GPU could be interesting, but currently we have 2, 3, 4, 5, something like that. What really helps is to improve the collision avoidance checks. So currently, if we, I also go to another scene here. If you see here, we have here a high model, so for example, and we are doing a mesh check. And this is quite expensive. So if we find a way to simplify the scenes using some primitives and still be quite accurate, then it will help us and we still can solve the task. So we need something better than mesh-to-mesh checks. And this, or you do the mesh-to-mesh checks on a GPU, that could be also interesting. And then perhaps we get it's fast enough to get it in real time. So under 4 milliseconds, for example.
Okay, thank you.